Okay, good afternoon. It's a great pleasure to introduce today's colloquium speaker, Professor Patrick Brady from the University of Wisconsin at Milwaukee. He's also the spokesperson of the LIGO scientific collaboration. Professor Brady's interests are in different aspects of gravitation, both theoretical and experimental. In particular, the search for gravitational waves from coalescing compact binaries and their electromagnetic signatures. He did his PhD with Werner Israel, the famous relativist, and was later a postdoc at Kip Thorne's group at Caltech. And when the LIGO scientific collaboration essentially formed during the mid-90s, and he was a member of the collaboration ever since. He played a really leading role in developing the whole paradigm for gravitational wave data analysis that is used in LIGO and Virgo, including the design of algorithms, software, as well as the hardware platforms where these analysis codes run. And has played several leadership roles in the LIGO scientific collaboration and the worldwide gravitational wave community. And it's great to have Patrick talking to us today. So without any further delay, let me invite Patrick to give the colloquium.
Thank you very much. Can everyone hear me? Am I working? Good. Okay. It's a pleasure to be here. I've enjoyed my few days. I'm leaving it tonight, so but it's been a lot of fun. So today I'm going to tell you about cosmic collisions and tell you a little bit about what we've learned so far about colliding black holes, colliding neutron stars, using gravitational waves to actually observe those things. Now, to start, this is the rough layout of my talk. I'm going to start out by starting pretty slow and just giving you a little bit of context for how we think about gravitational waves in the context of Einstein's theory of general relativity. I'll then move on to the meat of the talk, which is going to discuss the first gravitational wave transient catalog, and I'll give you an overview of the science highlights that came out of that. It was released just at the end of last year in 2018, and there's a few more results that have come out since then related to the data that was in that set, but mostly I'm going to focus on the contents of that data release. And then I'll finish with a very, very brief set of comments related to where we are today, which is only a few months later, and also where we're going in the next decade. So to set the scene for gravitational waves, here we have a picture of the mathematics that kind of underlies our thinking about space-time and about gravitational waves. This is the space-time interval, and in it we have the coordinates, which are the time and space coordinates we normally think of. We have the Minkowski metric, which indicates that if it was the only piece there, it would be flat space-time. And we're going to consider a very small deviation from flat space-time that we label by this h sub alpha beta, which we refer to as a metric perturbation. This is pretty much the most sophisticated math that you're going to see in the talk, so don't be worried or put off if you haven't seen it before and are a little unfamiliar. The key thing to note is we're looking at this thing, this perturbation, this fluctuation away from flat space-time. Now, Einstein, very quickly after he discovered his theory of general relativity, investigated the properties of his theory and what it said about how the fields propagated. And in 1916, he figured out the basics of gravitational wave generation and gravitational wave propagation in his theory. This is the quadrupole formula he wrote down more or less in 1916. He had an error, but he corrected it a couple of years later. It tells you that this metric perturbation depends on Newton's constant of gravity in the numerator. There's 4 powers of the speed of light in the denominator. It's 1 over the distance to the gravitational wave source, gives you the size of this metric perturbation. And then it's the second time derivative of the quadrupole moment. Now, to try and understand a quadrupole moment, I don't have my usual demo, so I'll try and do it with this slightly imperfect version of it. To try and understand whether or not something has a quadrupole moment, the way to think about it is pretty simple. If you consider this thing here, it's more or less a cylinder, so imagine for a moment it is. And if I take it and I spin it along the long axis, what you notice is that the shape you see from where you're sitting doesn't change. It always looks the same. However, if I take it and I spin it along the perpendicular axis to that, then you notice that there's a change in the profile that you observe. And you can tell as a result of that because when you look at it from a different direction, there's a change in the profile, there's a non-zero quadrupole moment. And so Einstein said that if you have an acceleration of that quadrupole moment, then you generate gravitational waves. And you can then sort of get a heuristic for this, which is Newton's constant divided by the speed of light to the power of 4, the amount of mass that's in the quadrupole moment, and then multiplied by the velocity squared of that quadrupole moment divided by the distance to the source. So this recipe for gravitational waves actually tells you what you need to do in order to generate strong gravitational waves. First thing, you need to get mass, m. You need a lot of it. Second thing you want to do is you want to put it into something that's distorted. So you want to put it into a lumpy form. I go with my fist as my first version of that. And then what you want to do is you want to accelerate it rapidly. So you need this v squared term. You need v to be very, very big. Okay? If you push it towards the speed of light, you're going to get the strongest possible gravitational waves you can. And then finally, of course, if you could vary the distance to the source of gravitational waves, as you get closer, they're stronger, further away, they're weaker. Now, the next thing that I want to tell you about is I want to just have this image in your mind, because we're going to come back to it later, of how nature might generate gravitational waves. This is a pair of objects, black holes. So we're going to think of these as two black holes orbiting around each other. Just the same way as a planet orbits around the sun or two stars in a binary system orbit around each other, you can get pairs of black holes orbiting around. And as they do, what you saw here was that they caused the curvature of space-time to ripple. And the changes due to the changing position of those black holes have to move outwards from where the black holes are at the speed of light. And so Einstein's theory predicted that you had gravitational waves which traveled at the speed of light. There were two polarizations, and we're going to see what they kind of look like in a moment. And this was his basic prediction. To measure gravitational waves, I start from this simple cartoon. I imagine I'm out in empty space, somewhere up in empty space, and a place, I'm sorry, it's a little dim here, but this little red dot right in the middle is going to just act as a center point so that you can use it as a reference. And out in flat space, I set up a ring of particles sitting in exactly a circle of radius little l. Now, if a gravitational wave propagates from the back of the room and propagates straight inwards and through the screen, then it causes that ring of particles to effectively change position relative to this central reference point. And so if I send the gravitational waves through, this is them cycling back and forth through the screen, just rolling on through all the time. So you get this stretching and squeezing in perpendicular directions, alternating back and forth as the waves go by. The strength of gravitational waves are talked about by taking a look at this this delta L that is caused by the gravitational waves. So there is a maximum stretching vertically, for example, or horizontally for that matter. And you compare that delta L to the original radius of the circle that you set up, and we refer to that as the strain, or the distortion. So it's the distortion of the original circle is a measure of the strength of the gravitational waves as they go by. And that strain, we often refer back to the metric perturbation H alpha beta. It's related to it. So the H is directly related to this strain. Now, it's always interesting to try and set a scale for the detection of gravitational waves or anything when you actually come at it first from a theoretical perspective. And Einstein, right away, when he was doing this back in the early part of the last century, he did some back-of-the-envelope calculations, and he actually sort of concluded, you know what, no one's ever going to measure these things. They're kind of irrelevant, but it was interesting to do the calculation. When people really started more seriously thinking about measuring gravitational waves from sources out in space, they did some other estimates. And they said, well, what if you could get the mass of the sun in two stars that could get really close together and orbit near the speed of light, and we're about 10 megaparsecs away or so? How strong would those gravitational waves be? And the number you come up with is 10 to the minus 21, which is the number that's sitting over here. And that's the ratio of the maximum change in length to the original length. And to put it in perspective, that's the comparison between the thickness of a human hair and the next nearest star to us at just over 4 light years away. So this distortion from an astrophysical source at what's actually a modest distance is incredibly small. And so the challenges of trying to measure that really came to the forefront in the late 50s and the early 60s, with Joe Weber first trying to measure it by using what are called resonant bars. So you would just get these masses that would interact as strongly as you could with the gravitational waves. When a gravitational wave would come by, it was supposed to ring the bar, like ringing a bell, and that was going to be a mechanism to detect the waves. It was unsuccessful, but then in 1972, Ray Weiss came along and he decided to try out this newfangled thing called a laser to measure certain distances better. And he came up with a design for a gravitational wave detector that was based in some way on intuition from that cartoon that you saw on the previous slide. The first thing that you do is you get your laser. And the way we use laser beams to measure light is, or to measure distances is, we basically have to measure how long the light takes to travel along certain directions and come back. And in this particular case, Ray Weiss decided, let's try out using this laser beam in an interferometer. And what we'll do is the red dot from the original, from my cartoon a moment ago is sitting here, and it's a beam splitter. So the laser light gets put onto the beam splitter, sent down 2 perpendicular arms. So each one of these things can be thought of as yellow dots that are at 90 degrees to each other on the circle in the cartoon. And the light gets reflected off them because they're made as mirrors, reflected back into the middle, gets interfered, and the device is set up such that when a gravitational wave passes, some light actually comes over onto a photodiode over here. So this beautiful animation from LIGO, first used at the announcement of the first detection of gravitational waves. I'll play it through right now. There's the beam being split. Now you notice the intensity of the waves at the photodiode is changing as the arm lengths change by gravitational waves passing. This particular perspective treats light as a wave, which is really how we analyze the system when we want to understand these instruments. You come back, you set it up initially so that there's destructive interference going on to the photodiode. A gravitational wave passes, changes the arm lengths, and that interference pattern then goes from being destructive to constructive. So that's the basic principle of a gravitational wave, a laser interferometer gravitational wave detector. Weiss set about getting some other people convinced that it was a good idea to build detectors like this. At first, he was interested in some prototypes, so they began to build some things that you could put onto small desktops. They went bigger than that, up to scales at the sort of few meters scale then for a while. And in the mid-70s, he and Kip Thorne got together and began to plot a course to propose to build a gravitational wave detector based on these principles that would be capable of detecting gravitational waves with strains around 10 to the minus 21. And in 1989, basically, the National Science Foundation of the United States first funded the Laser Interferometer Gravitational Wave Observatory, LIGO. Within the design, they had started from the principle that these things are so weak, and the one thing that's going to be very easy is that if someone happens to drop a wrench or a hammer in the room near one of the instruments, it can easily cause the instrument to vibrate and mimic gravitational waves. And so to be sure that they actually detected a gravitational wave and not someone just dropping a hammer, they decided that they needed to build 2 of these instruments. They also figured out that based on the technologies that they had at their disposal in the late 80s, that the basic sensitivity they needed to achieve, there was just no choice but to take a leap from something that's about the size of the table to take something to a leap. This is something that's 4 kilometers along each of the arms. And so right here in the middle, you have the corner station where the beam splitter hangs, the laser is there, the photodiodes, and of course, my little cartoon of a gravitational wave detector is incredibly oversimplified. All of the detection apparatus is housed inside of that corner station. The perpendicular directions are here. The mirrors are suspended. They're hung on seismic isolation systems at the ends up here, 4 kilometers away from the beam splitter, similarly down here. And so what you have is these really massive instruments, that one in the northwest of the United States and one in the southeast of the United States in Livingston, Louisiana. These are the instruments that detected the first gravitational waves. So this is a trace of that, and we'll talk more about it in a moment. This is the images that were used when the Nobel Prize was awarded to Ray Weiss, Barry Barish, and Kip Thorne for being the instigators and the leaders of this project. And the one thing that I always like to highlight is that there was another scientist that was involved in the very early conceptions of LIGO as a 4-kilometer detector, and that was Ron Drever. And Ron passed away between the time when we detected the gravitational waves and the Nobel Prize was awarded. And so he didn't actually get to share in the Nobel Prize after all. Nevertheless, there's no question that these 3 they were kind of exceptional contributors to this experiment. So let's take a look at where we were in 2015 when we were getting ready to turn back on the Laser Interferometer Gravitational Wave Observatory. And at that time, we weren't only working alone, we were hoping to work with the French-Italian group, Virgo, which have a similar detector in Pisa, near Pisa in Italy. They didn't turn on in 2015. It took them another year or 2 to get ready to turn on, but still, we were partnered with them at the time. I want to highlight that where we are today, there's another detector that's pretty advanced in its construction phase. It's the Kagra detector in Japan. It's an underground detector. It's really trying to push the limits of our technologies. It's underground, it's cryogenic, it's got all sorts of little bells and whistles. It's a really tough one to try and push because it's trying to use the cutting edge technologies, but it's coming along and hopefully they're actually going to join us running near the end of the year. And of course, LIGO India. In case you hadn't noticed, my LIGO India t-shirt. LIGO India is also slated to be built over the next 6 years, maybe 7, and come online in the middle of the next decade, and join together with the 3 currently operating detectors, Kagra, hopefully, and LIGO India, to give us a global network of gravitational wave detectors. So that's just a quick whirlwind tour of where things started from and also what we have in terms of gravitational wave detectors today. I want to now go and give you a little bit of the motivation of why to build these things and then say a bit about these sources called compact binaries. Binaries that contain stellar mass black holes or neutron stars. The motivations that we used to list before 2015 went roughly as follows. We were going to test relativistic gravity and develop gravitational waves as an astronomical probe. We had a list of anticipated signals. There were transient signals. Those are ones that essentially come, last for a little bit of time, and then go away. And in those, we had compact binary coalescence, we had gravitational waves from supernova explosions. We've got one of my favorites, which is cosmic strings that actually can send out bursts of gravitational waves, black hole ring down. The yellow here indicates the things that we've detected so far. And so you notice that then there's a whole host of other things that we thought about. There are sort of continuous waves which might come from spinning neutron stars that are just spinning all the time and have a small mountain on them. There's a stochastic background, which could come from sources that are distributed through the universe on cosmological scales, and the waves are coming at us from all directions, and so they mix together to form a cosmological background. There's some subtleties to how we think about that. And then, of course, there's within those sort of three classes, there is going to be things that we haven't thought about yet. At some point, we really hope something's just going to show up in our detector. We're going to be, what is that? It's definitely a gravitational wave, but we have no idea what it is. Now, the most important aspect of the motivations that I want to stress at this stage is that it was realized pretty early that gravitational waves carry sort of a unique perspective on the sources that are out in the universe. They tell us more about the sort of global structure rather than the sort of substructure of the objects. And they tell us about the dynamics of the sources. These are things that are not so well captured by just straightforward electromagnetic radiation or particles. Now, the really nice thing about this is that I've got another slide that I use sometimes which breaks this top bullet point out into a list of things that we were going to try and do when we detected compact binary coalescence and black hole ring down. And it's scary that after 2 years of observing with LIGO, we had checked the boxes on pretty much all of them. So within a couple of years, we really just had a tremendous set of breakthroughs. So let's take a look in a bit more detail at how this all works. So this here is a picture to give you a sense of a binary system. It's actually a numerical simulation generated by the SXS collaboration, where they've got two black holes, one slightly more massive and therefore represented by a larger radius and larger size. The other is smaller. They're going around each other. And what we're going to see is that as they go around each other, they generate gravitational waves. Gravitational waves carry energy. And so they remove energy from that orbiting binary system. And as a result, if you think about that, then you have to compensate for that removal of the energy somehow. And the way the system compensates for it is by the two objects getting ever so slightly closer together. So as the gravitational waves are emitted, the binary system gradually shrinks inwards. And eventually, the two objects crash into each other. What you're going to see down along the bottom is a trace of the strain, that distortion we were talking about earlier, as the binary system evolves. And this is what the trace will look like eventually. You'll see it going along here in blue for a while. But you notice that since this is the time axis and this is the strain axis, you notice that the period decreases, so the frequency increases. That's because the orbit tightens, and therefore they orbit more quickly, and the amplitude also goes up. This type of signal we refer to as a chirp. It's got amplitude increasing and frequency increasing. So let's watch this through. It lasts about a minute. And so you'll see that these things are going around. We don't see the gravitational waves within the simulation, but after a little while, you begin to notice that the objects are orbiting more quickly. You notice that they're getting a little more close together. And you start to creep into this regime where the frequency is moving upwards, its amplitude of the gravitational waves are going upwards, these things are orbiting more quickly, and then, bam, they crash into each other, they form a single black hole. It rings down really, really quickly, shutting off the gravitational waves, and settles to a final form, which we think is a Kerr black hole. So this is the basic principle of the type of thing we're looking for out in the universe. But when you look at this in more detail, you can start to ask questions about, well, how does this waveform here depend on things like the masses? We saw that this was a simulation with two different masses. How does it depend on where I'm looking at the source from? How does it depend on how the source is oriented relative to me? And you go through and you build up a list of the different parameters that are involved in trying to understand a binary system. And what you see is that if you imagine this is you with your coordinate system down here looking up at the sky at a binary system, you've got right ascension declination, you've got distance to the source, you've got the polarization angle of the gravitational waves as they come towards you. You have a time, which is some reference time of the gravitational waves. You have a reference phase. You then go up to where the source is, and you notice that there's a direction associated with the normal to the orbital plane. You have the masses of each of the objects in the binary system, and then you also have the three-dimensional spins of the objects in the binary system. So if you do a quick count of this, there's 17 parameters in total to describe the dynamics of this system. Okay. So in principle, by measuring the gravitational waves, you could in principle attempt to extract all of those. It's not straightforward to get at all of them, but some of them, it turns out, are. So there are certain combinations of the masses that are incredibly easy to get at. We can get at them very, very simply. The other thing that is nicely extracted is the distance. And that distance to the source is going to be important in some of the science results that I tell you about in the next few minutes. So this is the thing to be thinking about when you think about a binary system. You get the gravitational wave signal arriving at Earth, measured by the LIGO detectors, or the LIGO Virgo detectors these days. And then what we try to do is we take that waveform and we try to figure out what parameters in a binary system would have led to that waveform showing up in our detectors. And that's the problem that we have to try and solve when we take our data. So let's take a look at the last few years of observing. I'm going to start with what we refer to as observing run 1 and observing run 2. So short code for those are O1 and O2. This is a calendar starting in 2015, running up to August 2017. This is the first 2 observing runs we did. LIGO, the 2 LIGO detectors were operating during O1. We started in September of 2015 and ended in January of 2016. And O2, we started in December of 2016 and then ran up to August of 2017. You'll notice already there's a few markers on this particular image, which marks a few of the times when we detected gravitational waves. Those gravitational waves came from binary black holes. But you're going to see in a minute that there's a few more things that I want to tell you about as we go through this. So this is the time span for O1, O2. A couple of points to bear in mind. LIGO only operating during this period of time. LIGO only operating all the way up to essentially the 1st of August in the O2 era. So Virgo joined us only for the last month of O2. Turned out to be a very lucky moment for them to join. Okay, so now let's take a look at what we've learned since 2015. The very first thing, I just can never resist playing it. Some of you saw me give a similar talk yesterday, and I played this then. We're going to play it now. This is the first gravitational wave detected. It's seen in the LIGO Hanford detector. It's seen also in the LIGO Livingston detector. The traces here show time. You've got a half a second duration along the time axis, and each of them is broken into a frequency component as well, from basically 10 hertz down here up to 512, and then similarly up to 512 here. So what you'll see on the screen is you'll see a trace come across the screen, and like you'd expect from a merging binary, what you have is that the frequency of the gravitational wave starts out low initially and then sweeps upwards as the signal chirps up. And so you get a trace which goes through this plot like this. And then the other thing you're going to do is you're going to hear the sound. And the sound is the sound that was actually measured in the gravitational wave detectors, filtered 2 different ways. The first way was to suppress a bunch of noise and just bring the sound out. You cannot hear it like this without knowing it's there and knowing how to filter away some of the noise. And then the second time you'll hear this repeated, is we actually shift the frequency to make it a little more audible and a little more chirp-like, and you'll understand why in a moment. Okay. And because I can't resist overusing my same thing as I say every time, for me, that's the most beautiful sound in the universe. I'll never forget the first time that I heard it. It was just like, this is so cool. We detected this on the 14th of September. It was very near the beginning of the observing run, the first observing run. In fact, it was so near the beginning, it was before it started. We had actually been doing an engineering run leading up to the observing run, and we were just tightening all the bolts on everything, and we were running the detectors to just see what we found, and we found something. So that was really, really good. I remember about 3 days later, I was walking towards my office from home, and there's a little hill outside my house, and so as I was walking up the hill, I had this really big grin on my face. Now I was heading into the office at the start of semester, where certainly the faculty members know the weight of the world is crushing your spirit, but I still had this big grin on my face, and I wondered to myself, why have I got this grin on my face? And it suddenly dawned on me just as I got up near the top of the hill. It's like, wow, we detected gravitational waves from a pair of black holes that crashed into each other 1 billion light years from Earth. This is so cool. And it was really cool for me because the reason I started in this field was my interest in black holes as a kid, hearing about it through reading articles and watching TV shows. So it was fantastic to be part of this. But of course, it was just the beginning. And as we went through 0102, we built up a list of detections, which is exactly what you'd expect, given that we had that first one quite early. And we released this first transient gravitational wave catalog at the end of 2018. In the catalog, we, at that point, documented 11 events with a false alarm rate less than once per 30 days. For those who are less familiar with this terminology, the false alarm rate essentially means that when you set up your search and your observations of the data and you set up criteria for identifying things, whatever they are, in your data set, above a given threshold, the rate at which you would get things above that threshold for that arise not from the signals you're looking for, but from background noise, is less than once every 30 days. The other criterion we used, and the one that's most important for these 11 events, is this one. We have a way to estimate the chance of these events coming from an astrophysical source, and all of these had a probability of being of greater than 50% of coming from an astrophysical source. So we call these confident gravitational wave detections. 10 of them are binary black hole mergers, and one of them, a very exciting one for us, which I'll spend a bit of time on in a moment, is a binary neutron star merger. In addition to that, in the catalog, we released 14 marginal candidates. These had probabilities of being astrophysical less than 50%. And if we go to the next plot, which actually gives you a sort of a slightly closer look at the data itself at the end of our experiment, where the strength of the gravitational waves is plotted along the horizontal axis, and then the number count of things that we measure in our experiment is along the vertical axis. This here is 1, 10, 100, 1,000. If you see this trace here, this bluish trace going up, and then all the way up here, that's the trace of those things that come from noise, so that we consider those just background in our experiment. And then you can see that there's, if you watch the actual data, it comes down and it starts to have, the standard step like appearance going down here, and there's a big tail going out in this distance. And that tail is an indication that there's a set of sources in there that are not consistent with the background noise. They're labeled here. This was the 17th of August binary neutron star event, which we'll talk about in a moment. This was the first detection, so it was one of the most significant things in the catalog, and then there's a whole sequence of others as you go down there. The first thing that we learned from this was actually really, really interesting. We went in and we took a look. This graphic tries to give you an idea of what the masses were of the binary systems compared to, and by the way, the horizontal axis has no meaning. It just sort of stretches these things out to give you a visual. So these magenta type circles here correspond to black hole masses measured of objects in our galaxy. Okay, and so you'll notice the most massive is around 20 odd solar masses up here. Okay, so that's what we knew about before the first gravitational wave detection. But actually, and I can't remember which one it is. I think it's right here. Is the first detection, and you notice that the masses are really high. They're up there around 30 or 40 solar masses. Okay. So the first surprise with the first detection was, in fact, the masses of the binaries in it were much bigger than anything we had actually come to measure here in our galaxy so far. You notice then also that it actually stretches up quite a bit, and of course when you take two black holes, which is one binary system is two black holes that collides to form a third. So you take something here that has something like 20 solar masses and 30 solar masses, and you get something around 70 solar masses. And so you see that the spectrum of black hole masses is something that begins to unfold as we get all of these additional detections with gravitational waves. You also notice that this was 0102. Since this was all of the black holes we knew about before 2015, you notice we're really building up a list of black hole candidates and masses. This down here is the neutron star case. These are the known neutron star masses. All of them lie in this range between 1 and 2. There's some fairly high ones. The masses we measured for the neutron star binary down here around 1.5, 1.4 solar masses. The other thing to note here is that there's a gap. This gap in here in between. We think, of course, that when the two neutron stars collide and merge, they produce something that would show up in the gap, but typically we don't expect anything in this gap coming from standard stellar evolution. Supernova explosions disrupt things when they actually have progenitors that put them into that mass region. So this is another way to look at the gravitational wave transient catalog. Each one of these little frames corresponds to a numerical relativity simulation of the binary system that we detected gravitational waves from. The sound in the background has got pretty much nothing to do with gravitational waves. It's just intended to relax you. So here we go, taking a look at what's going on. Each of these is going to merge after a period of time. The waveform traces are being shown along the bottom. And so what you notice is that the different waveforms have different sort of numbers of cycles, they have different durations, they have different mass ratios and masses associated with the binary systems. And all of those things we can pull out by observing the data stream from the LIGO Virgo instruments and then also comparing these waveforms to what we see. That's another one of my favorites, a nice a nice uneven mass ratio, so it's a particularly lovely binary in that regard. So this could go on for a long time, but I'll run out of time for the other science, so I'm going to stop. You can find this online if you go to the LIGO Virgo website. There are links to it, and you can actually go and listen to it all day on YouTube. All right. So what did we learn? Let's take a look a little more quantitatively. This is a distribution of the masses of various binaries that we saw. You can note that there's one down here. This is the binary neutron star. Then you've got masses up here that are going up above the 10 solar masses pretty much, and then stretching all the way up here into M1, M2 being somewhere around 40, 50, 40, 40. Okay. So that's what we learned about the masses. Something I didn't explain, I should have. These lines represent contours of probability. Sorry about that. So inside of these contours is the place where we are most confident that the masses of each of the detections lie. Okay. So as a result, when I mentioned down here the neutron star binary, you can see it's right down the bottom in a narrow area, whereas the highest mass binaries that we detect, the uncertainties are much bigger up in that region. The next thing that I want to bring out is that we don't have any measurements of spin for black holes in any other ways as yet. And we've been able to try and make some measurements of the spins associated with the black holes that are in the binary systems that merged. This plot is a violin plot. What you have is a parameter which represents the size of the spin within the binary system, going from a possible maximum of +1 to a possible minimum of -1. The -1 just corresponds to the directionality, essentially. And what you notice here is for each of these little things corresponding to one of the events, doesn't matter which one, so let's see if we can find the first one. So here's the 14th of September 2015. These sort of little bubbles indicate where the probability lies. And so you can see that for that event, the most likely place for the chi-effective was to be close to 0. And when you look at all these events, what you notice is we only have one that's starting to have some evidence for creeping up in spins. So typically we see things as if, at least so far, as if the spins are actually pretty small on these binary systems. Distances, it's good to just get a sense of the scale at which we're able to observe now. For the binary neutron stars, it's still rather close by, so it's down here in the megaparsecs. However, for the most massive binary black holes, we're seeing out to multiple gigaparsecs and are beginning to approach z=1. So we're actually getting to see a fairly big part of the universe as we go at the present time. One of the most important aspects of this for us starting out was to take the observations from 01 and 02 and to try and understand how often a pair of black holes like these are colliding in the universe, okay? And so you can do, first of all, the easy calculation, which is do an experiment that lasts for a given amount of time, count how many binaries you get, and then, of course, the number divided by the time gives you a rate. So that's the first thing you do, but then you have to figure out how sensitive to the universe you are. So you have to figure out how far out you can see, how much space-time volume you actually measure. And so what we do is we take the number counting and we turn that through a set of mechanics into a statement about the occurrence rate of binary black hole mergers in the universe as a function, or pardon me, in terms of gigaparsec per gigaparsec cubed per year. This graph is a probability on the vertical axis. And then there are two curves that are really shown that you need to worry about. The first one is this one here, which is a posterior on the rate, which comes in somewhere down here around 20 times 20 per gigaparsec cube per year. The prior on that is flat in log of the rate. And then if you put in a power law in there, then you actually get a slightly different answer. It doesn't really matter too much for us. The bottom line is that when we look at this, what we see is that we're into 10 to 100 per gigaparsec cube per year. Nice sort of little calculation to do there is to realize that that translates into very roughly a binary black hole merging somewhere in the universe every 10 or 15 minutes. So quite nice. Another thing that we get to do with the catalog is we get to ask questions about what's the smallest mass of a black hole and what's the biggest mass of a black hole. This plot up here attempts to summarize our results for that. You've got mass going along the horizontal axis from 5 solar masses up to 50 solar masses. And all of these curves represent various interpretations of the mass spectrum that we can infer based on the number of of binaries that we've observed so far. Within this plot, you notice that it sort of dies off for most of the cases, not all of them. Some of the models that we choose to test don't have a fall off, but most of them indicate some sort of fall off down here, and there's also a fall off for all of them up here at the upper end. Now, this is a very preliminary investigation. If you think about it, we only have very few black hole measurements so far. And so what we're doing now is we're accumulating more, and we'll be able to do a much better job with O3. So I want to spend a few minutes before just finishing by telling you about where we are today with O3, discussing the 17th of August event. This was the first time we detected a neutron star binary merger, and we got lucky because it turned out that it was somewhat nearby, and in fact, the gamma rays caused during the collision were also detectable and were found by the Fermi Gamma Ray Burst Satellite. And so if I play this signal goes from 6 seconds before the merger to the merger, followed by the gamma ray burst at 1.7 seconds later. It was tremendous to get this event. I also like to put this slide in because, of course, you absolutely know why there's a picture of someone cycling a street in Amsterdam. This was my view from my laptop because the day that this happened, I was walking around Amsterdam with my wife, and suddenly someone contacted me on my phone to say, hey, we've got this really cool signal. And so I was sitting there frantically trying to figure out what was going on. And I thought it was very exciting. And I took that picture just to have a reminiscence for it as time goes by. Here we have the mass distribution as observed from GW 170817. You can notice, I'm not going to go through too many details, it really doesn't matter. The sort of region in which we think it's most likely to be is up here in this region here. It's in the range 1.2 to 1.4 and 1.25 to 1.5 or so. So this is a very typical vanilla neutron star mass binary as we detected it. Within an hour or so of detecting that event, we sent out a notification to our astronomer partners to start observing the sky to see if they could see the flash of light that would be associated with the collision of the two neutron stars. And this animation, which was generated by Varun Bolero for the Growth Collaboration, shows 1 second for every 0.2 days passing. You've got the Earth, and then you've got day and night. And what you'll see is, as it goes by, you'll see certain telescopes be indicated by sort of little bubbles flashing. And that indicates when different telescopes were able to observe the sky in the direction of the gravitational wave source. And you'll notice that about 10 hours after the source, there's a flash that occurs down here in South America, and that indicates the first identification of an electromagnetic counterpart to a gravitational wave. So bam, it was found that very first night, about 10 hours after the merger. You can notice that observations continue, and this animation goes for about a month after the observations, and you just see that observations are continuing all around the world. This was a huge effort. By the time we were done and wrote a paper with everyone who had done any observations, there were nearly 5,000 authors on the paper. And it was really, really a fantastic set of discoveries. Now, the things that we learned right away by looking at this source were just amazing. Internally in LIGO Virgo, we knew pretty much at the get-go this was a binary neutron star merger. So we had a good sense of the masses, we had a good sense of how far away it was, we had some sense, although way too much of the sky was visible by our detectors. But the counterpart was found 10 hours later. So this is the discovery image from the 1 meter 2 hemisphere collaboration using the SWOPE telescope down in South America. This is NGC 4993, now a very famous galaxy, not so famous beforehand. It's at about 120 million light years away. And when in this discovery image, right, you see the blob of the galaxy, and of course you see other little stuff, and in particular, if you didn't know better, this would just look like anything else on the image. But that night, the astronomers that took the image were able to take their image and compare it to pictures of that galaxy that had been taken previously at other times. And they did sort of the quick look method, which is essentially to blink the images to try and see whether or not something was there. And I'm going to show you this in reverse because I have an image that matches taken with the same telescope 4 days later when the source had dimmed. And if you watch, you'll see it blinking. Okay, so just watch the blinking here. So that blinking is essentially the way that they identified that counterpart and then quickly wrote up and told all of the other astronomer partners, hey, by the way, NGC 4993. The good news is a few of the astronomer groups that had big telescopes continued looking all over the sky, but the other groups that actually only had narrow field of view telescopes zoomed in on 4993 right away. And we began to take some of the best data ever for an astronomical transient. This was followed for over a year afterwards, and we've learned a great deal about what happens in the post-merger phase as a result of the electromagnetic observations. I want to highlight a couple of really cool things. Here's one, which is that we actually can, by putting together the time delay between the end of the gravitational wave and when the gamma ray burst is seen, with the distance to the galaxy, you can just very quickly, you can do it in the back of your envelope or your hand even right now, and you can just estimate what's the difference between the speed of light and the speed of gravity. And when you make the estimate, you come up with a number that's around 10 to the minus 15. It's actually a bit less when you do it much more carefully. So this experiment took us from knowing that the speed of gravity and the speed of light were fairly similar. The numbers the day before this event were somewhere around 10 to the minus 3, 10 to the minus 4. But the day after, it was 10 to the minus 15. That's a pretty dramatic measurement. I love it because it's so simple, but it's also really, really cool. The other one that we got pretty much right away with that same reasoning is that with the gravitational waves, we could measure the distance to the source. Knowing the distance to the source and having a galaxy where we can measure its redshift very easily, we get to use Hubble's law to extract the Hubble constant through a new and independent measurement. And this is our first result on the Hubble constant. We've had actually multiple approaches since, but this shows a probability on the vertical axis, the Hubble constant in units of kilometers per second per megaparsec on the horizontal axis. The sort of very pale red and green here are the current results from Planck and from the supernova project. And you notice that our posterior distribution has this lovely thing that peaks right in between the two of them. Now the error bars are huge, right? Our 1 sigma error bars put us at having a peak around 69 or so, and then put us with the 10 on either side. But still, this bodes well. By making more detections like this, we can narrow the error bars, and over time, we can get a better and better measurement of the Hubble constant through a totally independent means than those other two. I'm going to skip this. Oh, actually, no. Let me just give you this one very quickly because I like the round number of it. The other thing we were able to do, similar to the rate calculations we did for the binary black holes, is with the neutron star binary to estimate how often these things merge in the universe. The basic answer is they merge once per million years per megaparsec cubed. Okay. Turns out that number is kind of interesting because there was a paper by Sterl Finney way back in 1991 which predicted the rate of mergers of binary neutron stars. He essentially said it was 1 per million years per megaparsec cubed. So it's really nice that so far it hangs in there. Of course, in this case, we've only detected one such event, and so the uncertainties are still very large and we need to improve on that. Now I'm going to skip, because I'm going to run out of time, over a couple of other things just very quickly. We actually get to learn very interesting things about the internal structure of neutron stars as a result of this merger. So we can measure the mass and the radius. So we get to get a relationship between these, which then allows us to actually constrain the equation of state. I won't go through this figure because it'll just get too busy. The other thing is that one of the great mysteries that was beginning to be sort of understood that it existed in recent times is that when you look at the periodic table of elements, we can explain a lot of them. But before 2015, it was uncertain where all of these bright yellow elements came from. In particular, if you look, gold is in here. I can never find gold. I always want to find it. It's in there. You'll find it. I should know where it is, but I don't. So gold is in there. And, you know, the fun sort of estimate it's not necessarily accurate, but the fun estimate for that particular collision and how much gold was generated in the post-collision is about a Jupiter's worth of gold generated in the collision. It's kind of nice to think about it that way, isn't it? It's like maybe we'll go mine it. It'll be kind of fun. Anyway, so we now know something about the origin of the elements that we didn't know before. That will become better because, of course, whether or not we've really understood the origin of those heavy elements depends a lot on what the rate of mergers are in the universe. And so we need to measure molar of them, and we need to tune up those rates. So I'm going to finish now by just telling you a little bit about where we are today. We're in the middle of observing run 3. The LIGO and Virgo detectors are taking data in unison since the 1st of April, and we're going to run for 12 months of data acquisition. So far, we have 22 candidates that were identified in low latency. Low latency means that basically we had announced them to the public after about 6 minutes of the time the gravitational wave went by Earth. There's a few extra details in there that are not overly important. The black hole detection rate itself is now at about 1 per 5 days. We have one confident binary neutron star so far, but have no counterpart to it. And we also have one low significance neutron star black hole candidate that still sits in there. I like this graphic because it sort of gives you a sense of what was going on for us since April. So this is April 1st up here, I believe. Let me get my days right. Yeah, this is a Monday. So this was April 1st. We started public alerts on the Tuesday, and our first public alert and our first detection in 03 came just a couple of days later. Each time you've got the gravitational waves coming through. A really nice thing for a physicist is to go into a month like this, where you get a nice detection at the beginning, and then the weeks tick by with no detections. And of course, the physicist in you goes, it's Poisson statistics, that's totally fine. By the time you roll into the 4th week, the gut starts to just be a little in turmoil. Do I really believe that head of mine that Poisson statistics is right? But in the end, nature came through and gave us another gravitational wave just at the end there, and went back to normal rates of detections. So this is how things look for us these days. We tend to, every few days, have a new event that we have to be grinding through and trying to understand and extract all the parameters from. It's really fun. Some of the stuff is kind of different, and we're trying to do our best to identify special candidates. We have a way that we look at okay. Should I stop it or will it stop? I'm just about done. So we have a way that we look at the candidates. You can talk to Shashvath about this if you'd like to learn more about it. We actually have probabilities of what type of events they are, and these are just some little summary plots that indicate what we think. And so these are all of the binary black holes. We actually do have 2 things sitting here that are kind of in the BNS or NSBH category. This is this one that's a low significance NSBH. And we also have one that's clearly a terrestrial at this point, or most likely terrestrial. So looking forward, this is where I want to finish, is right now we're in the middle, or actually we're 4 months into 03. We've got 2 more months to go before that the first half of it ends. We'll take a commissioning break, and then we'll run for another 6 months. We anticipate having, by the looks of it, of order, probably somewhere around 100 to 120 detections by the end of that, which is just fabulous for us. We're really excited. And then we're looking into the 2020s. And in the 2020s, we hope to have a network that has the 2 North American LIGOs, LIGO India, Virgo, and Kagra, all operating simultaneously around the world taking data. So I'll finish at that. Thank you.
Thank you very much, Patrick, for this really exciting summary. I hope we can take a few questions. Hi,
it was a great talk. I just wanted to ask a question about the differences after merger of black hole binary and a neutron star binary. and whether there is any possibility at some point to be able to understand how the neutron star actually goes over into a black hole at a critical radius.
It's a great question. So there's a couple of things to note, things I skip over quite readily in these types of talks. The gravitational wave frequency when the two things merge is a function of the mass of the two objects. And in particular, the more massive, the lower the frequency at which they merge. And so for the neutron stars, the merger frequency is quite high. It's up in the kilohertz region. And the LIGO and Virgo detectors, the ground-based detectors, have reduced sensitivity up there. Now, we did take a crack at trying to see with the neutron star binary, could we say anything about post-merger oscillations, long-lasting signal? We didn't see anything. So our paper reports a null result. We couldn't. Now, it isn't to say they aren't there. It's just that really our sensitivity was not adequate to pull it out. So they weren't strong enough for us to see. It's going to be challenging, I think, with the current instrumentation, because realistically the mergers and those high frequency oscillations are so high that they really are buried under the high noise. People are trying to undertake a number of tricks to link together multiple signals to be able to pull out the weakest signal and take multiple binaries, but we don't know yet how that's going to work. So I think in the current generation, we'll keep trying, but I think it's a long shot. But future generations, there's a number of possibilities, right? So for example, there is the possibility that you can actually set up your interferometer so that you detune it, so that you get increased sensitivity at the higher frequencies while sacrificing sensitivity at the low. Now, if we got all of these detectors operational, you might consider taking one of them and doing exactly that. And so you might consider that, okay, we'll really dig deep, we'll be able to make the detection with the other four, and we'll do this experiment to actually measure these waves and see if we can tell a difference. It isn't clear whether that trade-off's the right thing to do yet, but it is still something that we think about and we think we might try and do in the future.
Hi. So I was just wondering, now that you have so many numbers, I mean, you have about 30 or so events of black hole binary mergers. Can one begin to see some pattern in the efficiency rates of conversion? I mean,
of stars.
I meant the efficiency rates of conversion of mass to energy, just in the merger, because they're typically of the order of 10%. There are theoretical bounds on how much it could be, and so on. Yep. So how is there some good statistics on that, and whether it's better when they are smaller or when they are bigger, the fraction that's converted to radiation?
Yeah, so that fraction actually doesn't really vary with those parameters, at least in the frequency bands we're in. It's actually a fairly small mass range that we're changing things in. I don't remember, Bala might actually, or Ajit might actually remember more.
There's no direct way of probing this energy radiated from the gravitational waves. You need to have simulations, and we know that they scale inversely with mass ratio. The equal mass ones are the most energetic, and the extreme mass ones are the least energetic. And again, they increase with spins also. These are known from numerical simulations. They're hard to probe through the fitting.
And that's what we have. I mean, I think a lot of the measures that we do for consistency, even the ring down to and final mass and so forth, they're based on these parameterizations. So you're really just cross-checking that the numerical waveform matches well onto what you saw. It's always consistent with this few percent generation based on the theoretical models so far.
Hello, sir. It's like, okay, I have one question. If a space-time distortion should travel at the speed of light, why do gravitational waves travel slower than light?
So within the context of Einstein's theory, His theory actually says it starts out by building in the speed of light as the maximum propagation speed, and anything that's got 0 rest mass will propagate at that speed. So as a result, when you go to the weak limit, so the very weak wave limit for gravitational waves, you see that they travel at the speed of light according to general relativity. So in general relativity, it says they should travel at exactly the same speed. And distortions of space-time are essentially that. They are, now, I want to be a little careful. It's not quite true, because if you just change a configuration, it does have to then change the curvature. But that change propagates away from the source at the same speed as light. So according to Einstein, we now know it propagates at the same speed as light to 1 part in 10 to the 15. So.
Hello, sir. Thank you for the talk. And my question was, from these observations or from the theoretical models, how can we estimate the probability of the elements that we get post-merge? Like, what are the methods which are involved in such processes?
So I'm not an expert on the methodologies for doing those calculations, but they're pretty, I don't want to call them standard because they are hard. They're standard, very hard nuclear physics calculations. So you take inferences about rates of reactions, you infer what the distribution of the types of matter that are present within the post-merger collision, and then you calculate the rate for certain reactions that occur in there. And so in recent years, Metzger has been one of those people who has led the charge on being able to do those calculations. And pretty much the sort of, when you took a spectrum of the post-merger explosion and you compared it to some of Metzger's simplest models, he had sort of chosen the elements that he thought would dominate the brightness of the source. And when you do that, you find that the peaks match pretty well. He had done the calculation for the lanthanides, which in the graphic I'd shown were in the graphic I'd shown, it's the one that was in the white box down the bottom. It's these ones down. It's these ones down here. He basically chose 1 or 2 of those and actually did a couple of reaction calculations and then calculated what the spectrum should look like for emission from those systems. I'm not an expert, but I encourage you to start by looking for Metzger's papers and look around.
In the initial slides, you had mentioned the kind of data that you want to look at and the kind of events that you're looking at when you were proposing the whole idea of LIGO. So one of the ideas that was put forth was, let's say, supernova explosions observing. So in case of, let's say, binaries, right, we have the whole frequency as a chirp. So, and what sort of signals would we anticipate or expect in case of a supernova explosion or other cosmic events?
Yep. So the supernova, there are calculations that have tried to take relatively sophisticated, but not the most sophisticated simulations of the supernova explosion itself, and then use those with general relativity or post-Newtonian type models to predict what the gravitational waveform should look like. Typically, the situation is that most supernova explosions that have been able to be simulated so far tend to be fairly symmetric. And as a result, they don't have a large quadrupole moment that's time changing rapidly. So first of all, the waves are actually going to be very weak based on our current knowledge. Now, having said that, that's sort of the best guess mechanisms for supernova explosions. And we think the waves might only be strong enough if the supernova explosion occurred in our galaxy. But if you start to get a little crazy, which Theorists can get crazy, it's okay. You can get crazy and you can explore parts of the parameter space. And when you do that, you can start to make predictions that you might get little blips. I mean, these are blips of gravitational waves. They've got a few cycles. They're not clean because they really depend on the local environment a lot more. But some of them, you might be able to see them if you could figure out a good detection method out to around 10 megaparsecs, which is actually not a bad volume. So at the very extremes, they could end up being detectable. They're hard to get at because they can be confused for background, or that type of signal could be confused for background, although we have methods that target exactly those types of signals. So little blips, they last for milliseconds. The good news is, if it ever happens in our galaxy, we'll probably see the neutrinos coming from the supernova explosion at the same time. And so we'll have the extra evidence for the time. We'll know where it is, probably. And so we'll be able to detect both the gravitational waves and the neutrinos. For things outside of our galaxy, right now the hope is fairly small, but we go for it and we try, because you never know when that crazy theorist had the right idea. So.
I wanted to know about, can the gravitational waves tell us about the interior of a neutron star? And what can we know about it?
Yep. So it can, and I don't have our most recent results in my talk, so I can't flip to the slide, but the basic principle is as follows. When we measure from gravitational waves the parameters of the binary system, we use the phase of the gravitational waves to tell us the information. So when we start to calculate the rate at which gravitational waves draw energy out of the system, we start making that calculation. Leading order term depends on the masses, and then as you crank along, you find other terms coming in, spins and so on. You also find that tidal deformation of the neutron stars relative to each other starts to creep into that phasing. And so that sets up a change in the phase that we can extract, and it's related to a ratio of the mass of each neutron star to the radius of the neutron star. Okay, so the coefficient that we can get at is related to that. And so when we do models of neutron stars, what we normally do is we fix an equation of state for the interior of the neutron star, and then we ask the question of what are the radius and mass of the corresponding neutron stars that we can get for that equation of state. And so that gives us curves going through a mass radius plane. Okay, and so as a result then, when you take the measurement of this thing, which is called the tidal deformability, you can overlay that onto those curves, and it starts to tell you which ones are allowed and which ones aren't. Okay, and so the plots I had here are a slightly different look at it. I don't want to say too much, but the radius is along this axis, and this is the radius of the neutron star. The mass of the neutron star is along this axis. And then what we have here is, this is for the two different binaries, and this is one of the early results. There's some really nice, more recent results as well. But these are the types of exclusion regions that we're coming up with at the moment. And so the bottom line is that the mass radius of the neutron stars lies in here. And so what that tells us is that for any equations of state that lie outside of these regions, right, then they're probably not allowed. Okay? And so this is the approach at its essence. We're getting more sophisticated at how we can get at that, and therefore we're able to say slightly more about those equations of state. There is another place where we actually get to fold in information. So for example, when you start to see an electromagnetic counterpart, you can actually start to ask, well, what does the nature of the neutron star have to be in order to generate enough material being sent out to actually generate a bright kilonova afterwards, and so on, okay? So then you start stitching those pieces of information together, and it gives you even better constraints. So this is really the early days in what we're going to be able to do with this. It looks incredibly promising. It jogged a lot of interest from a lot of nuclear physicists who are interested in dense nuclear equation of state, and they started to become interested in what we might be able to do in the coming years.
Thank you, sir, for the lecture. My question is, apart from the traditional interferometer, are we planning something else, some other technologies which can detect the distortions in space and time with such an effectiveness or efficiency?
So there are ideas. Most of the detectors that are planned to use lasers. So I didn't give you a sense of even the frequency ranges, except that you hinted at it, that it's sort of audio frequency range by playing the sounds for you. But when you start to look at the different frequency ranges, Earth-based detectors detect in the kilohertz regime, 10 to a kilohertz. When you go out into space using lasers, you can get down around 10 to the minus 4 hertz. And if you keep looking for methods, one of the most fascinating ones is this one, using pulsar timing. Doesn't use any lasers. What you do is you look for pulsars out in the galaxy, and you get your telescope, and you time how the pulses arrive at you. And then you build up models for anything that's intrinsic to the pulsars themselves. And what you watch for is, if you've got gravitational waves that are now in the nanohertz regime for this, passing by across these pulsars, what it causes is slight deviations that are correlated in the time interval between the pulses coming from the different pulsars. And this method has now been pursued pretty aggressively. The International Pulsar Timing Array, which is made up of both the North American Nanohertz Gravitational-wave Observatory and also the European Pulsar Timing Array and the Southern Pulsar Timing Array, are all trying to measure gravitational waves using pulsar timing. So this is a fascinating approach. It's limited in the range that it can go, so it's nanohertz, and so it's targeting not the type of black holes I was talking about that are stellar mass in the ranges of tens of solar masses, but it's targeting supermassive black holes in the 10 to the 6, 10 to the 8, 10 to the 9 solar masses. Okay. Now, after that, there's a very preliminary set of thought experiments, I would call them really right now, although some experimentalists are trying to do things, where they do what's called atom interferometry. It's not quite the same thing, and it's pretty complicated to try and build an apparatus for it, but they're working through the numbers to see if they can actually figure out a way that might be made sensitive, and then might be made sensitive enough to measure gravitational waves. Other than that, I don't know of anything else that's really in play as a workable. LISA is the space-based one at 10 to the minus 4, but it still uses lasers. And so so LISA uses lasers again. So the problem is, I don't know anything that's not lasers beyond the pulsar timing array that actually has a chance at the moment.
So in fact, I was curious, because you mentioned Joe Weber's initial experiments. Is there a way in which you could make that idea work?
So fundamentally, the sensors have been the limits there, and so it's sort of been a thermal noise problem that really, in the end, just has limited the sensitivity of those. So as of now, there's no good ideas to drive that to the really required sensitivity. And pretty much any of the structures they have, they're resonant in a very narrow frequency range, which also sort of their utility is less as well, even if you could get them to work. So yeah, so far that's actually an abandoned technology for detecting gravitational waves.
Sir, so the signals that we have detected, do they perfectly match with the theory, the computations what we get? That was my question.
Yeah, good question. Again, another item that I couldn't show, but I get a lot of extra.
Are there anomalies or something like that?
Yeah, no, I get a lot of extra time for the questions, which is perfect. So one of the things we do, and the group here is involved pretty heavily in it, is trying to look for deviations from the theoretical prediction, and by playing a few tricks. So we try and test general relativity. So far, we have nothing that shows any evidence of a deviation, and so we'll keep looking. It's clearly a big hope of ours that we could find something that would be an indication of where we should go next with our theories of gravity. But right now, the preliminary investigations aren't showing anything. It's a very promising area for theoretical considerations. I think it's a very hard area, but the point is that it needs a great deal of control over the waveforms, a great deal of control over the experiment, And so when you try to do something like that, you really need to understand things very, very well. So it's kind of a good area, especially on the theoretical side.
I think with this promise for this future, let's conclude this session, and let's thank Patrick once again for this very nice summary.
Thank you.